Alright, Finn, let's do this. We are going to cover all the remaining lessons that you haven't finished from Algebra 2, and I just want to assure you that you getting up to Lesson 104, you're going to be fine moving into Advanced Math. Okay? The purpose of this video is just to give you a little bit of a quick summary, a quick lecture on the remaining lessons that you didn't get to, so 105 up to 129. And I'm just going to pick problems from the remaining lessons that come from those lesson numbers, okay, 105 to 129, and I'll just try to go through some of them, give you a sampling, and I'm confident that you're going to understand what I'm saying and what we're doing, and you can find problems that have those lesson numbers attached to them, and you can practice them on your own if you want. But I'm also confident that if you don't pick up everything from this video, if you don't understand everything, you're still going to be fine going into Advanced Math because you're going to see it again and you're going to build upon it, and I can fill in the gaps if you ever come across something you don't understand later on in the next level of math. Okay? So, we're going to try to do this quickly, we're going to try to do it painlessly, and we're going to try to cover lessons 105 to 129 in the next hour or two. Okay? Really condense it and get you moving ahead so you can get to the next level and leave Algebra 2. Well, you're not going to ever really leave it. You're going to just be confident that you can build upon your knowledge and go on to Advanced Math. Okay? Alright, so I'm going to pull from lessons 110, 115, 120, 125, and 129, and I'm going to be looking at only the problems that come from lessons 105 up to 129. Okay? So for example, right here, number 1 in lesson set, or problem set 110, says R, J, and Cheng noted that the sum of the digits of the two-digit counting number was 9. If the digits were reversed, they found that the new number was 27 less than the original number. What was the original number? Okay, the key in this problem is to understand that we're talking about a two-digit counting number, and the problem is broken down into actually talking about the actual digits. So we have, in a two-digit counting number, you have a digit in the tens place and a digit in the units place, or ones place. So I'm going to use T as the digit in the tens place and U as the digit in the units place. And it tells us here that the two-digit counting number, the sum of the digits of that number is 9. So that means T plus U is 9. Okay? Then they found that if the digits are reversed, so that means T is normally in the tens place, U is normally in the units place. Now we're going to take that digit, whatever that is, 1, 2, 3, 4, 5, 6, 7, 8, or 9, that is in the units place, and move it to the tens place. And the tens digit is going to be moved to the units place. So when those digits are reversed, they found that the new number, not the digits, but the actual value of that number, is 27 less than the original number. So how do we represent these numbers, not knowing what they are, but just knowing that there's a value in the tens and a value in the units? Well, if the digit is in the tens, then it is 10 times that digit to get its value plus the unit. That would be the actual value of the two-digit counting number, 10t plus u. That's the original one. The new one, the reversed one, would be 10u plus t. And what did we know about the reversed and the original? The new number is 27 less than the original. So here's the original, 27 less. We're going to take 27 away from that and get our new one, which is 10u plus t. Now, what you're going to have to do is you're going to have to solve this algebraically. I'm not going to do that right now. I'm going to assume that you know how to solve a two-variable, a two-equation, two-variable system of equations here. So you're going to solve for one of these. You can use either substitution or elimination, but the first thing you might want to do is to get all the variables on one side and all the numbers on the other side. So for example, I'm going to subtract t from both sides and get 9t, and I'm going to subtract 10u from both sides and get minus 9u equals 27, and you're going to take these two equations and solve them for t and u, and that will give you the original number then. Okay? You can try number 2, which is going to be very similar to that. Let's jump down here. Let's look at this group here. We have number 6 from lesson 110, and it says graph on a number line. Okay. So if we take this right here, what we want to do is you want to look at regions for this one. So for what I mean is, you're looking at this and you're saying something times something has to be greater than 0. In order for that to occur, meaning it's positive, that means this number has to be positive and this number has to be positive, whatever they are, or they both have to be negative. Positive times positive or negative times negative is going to be giving you a product that's positive. So what we're going to do here, hold on. Okay, sorry, I got interrupted there. So as I said, you're going to test different regions. So you have either positive times positive or negative times negative to give you something greater than 0. But what you want to do is you first want to see where is this product equal to 0. And that's going to divide your number line into regions that you will then test. So where is x plus 2 times x minus 4 equal to 0? Where is that happening? Well, that happens when either of these values, these factors that are in parentheses, are equal to 0. Because 0, if this first parentheses value is 0, times anything would be 0. So you're trying to figure out when would this product be 0? Well, that's going to happen when x plus 2 is equal to 0 or when x minus 4 is equal to 0. Either of those situations will give you a product equal to 0. So that happens when x is equal to negative 2 or when x is equal to 4. So we take our number line and we plot those points. So if this is 0, there's negative 2, there's 4. That's where it's equal to 0. We don't want to be equal to 0. We want to be only greater than 0. There's no bar here, so you cannot include those points. You need open circles at negative 2, open circle at 4. Now all we do is we've divided this number line into regions. The region far to the left of negative 2, in between negative 2 and 4, and far to the right of 4. You're just going to test those regions now. For example, if I take the number 0 right here and I put it in, 0 plus 2 is 2, 0 minus 4 is negative 4, 2 times negative 4 is not positive. So this middle region is not going to work. It's not going to work. You will not shade that middle region. That means the region on the extremities is going to be your answer. We can test it. Take a number less than negative 2, like negative 3. Negative 3 plus 2 is a negative 1. Negative 3 minus 4 is a negative 7. Yes, negative times negative is positive. This region does indeed work, and we shade it. Okay? You can test the other extremity. It's going to work. 5. 5 plus 2 is 7. 5 minus 4 is 1. Positive times positive is indeed positive, and you shade it. Done. Okay? You can try number 7 here. The only difference is that you first have to factor it. So you want to get x squared minus 4x, bring the 5 over to the other side, minus 5 is greater than or equal, notice the equal bar there, 0. Factor this, and then do the same thing I did. So you're looking for factors of negative 5 that add up to negative 4. X minus 5 times x plus 1 greater than or equal to 0. Okay? Now it's exactly like the one I just showed you here, and you can finish it up. Just notice that this is saying equal to 0. So the difference is going to be you're going to have closed-in circles here, whereas I had open circles. Okay, let's come down here to 9 and 10. Both of those are coming from lesson 109. They are very similar problems. I'll just point out a few differences. This one right here is showing you you have a difference here that is being squared. That squared means that whole thing in parentheses is being multiplied by itself. So I'm going to write that out. X to the 1/2 minus y to the 1/4 times itself. X to the 1/2 minus y to the 1/4. And notice that's what you have here. Okay? So the only difference is that this was written in a condensed form because it is a binomial times itself. So they could write it as that binomial squared. Whereas this is a sum and a difference. So you're going to do the same process, just I had to do one more step here to start number 9. So now we're just going to multiply the first parentheses by the second parentheses. First binomial times the second binomial, and you're going to use FOIL. First, outside, inside, last. So the first ones have to get multiplied together, and when you multiply powers, you add the exponents. So x to the 1/2 times x to the 1/2. 1/2 plus 1/2 is 1. You normally don't write the 1, but I'm going to write it there just so you see we added those exponents together. And then outside, x to the 1/2 times a negative y to the 1/4. They don't have the same base, so you can't really multiply them together. We're just going to write them next to each other to show that they would multiply together if we knew what x and y were. So minus x to the 1/2, y to the 1/4. Inside, negative y to the 1/4, x to the 1/2, minus x to the 1/2, y to the 1/4. And then last, this is negative y to the 1/4 times negative y to the 1/4. So negative times negative is positive. Y to the 1/4, y to the 1/4. You add exponents when you have the same base. So 1/4 and 1/4 is 2/4 or 1/2. These are like terms. They both are x to the 1/2, y to the 1/4, x to the 1/2, y to the 1/4. Minus one of them, another minus one of them. You can combine these two together and get your final answer of negative 2x to the 1/2, y to the 1/4, plus y to the 1/2. That is as far as you can go until you know what x and y are. Okay? Okay, let's look at number 11 and 12. I'll do 11, and if you want, you can do 12. This is coming from lesson 108. So we're going to factor 8x to the 9th minus y to the 6th, p to the 3rd. Okay, the first thing you always do when you factor is you always look for a common factor, meaning is there something that is common to all of the terms in this expression. There's no equal sign here. You're not solving for anything. You're just simplifying. You're just using a method of simplification that may help in the long run. Okay? So you always look for anything that is common. So in this case, this has x terms. This one does not. That is a value of 8. There's no value except for 1 there. So there's nothing common here. Okay? The next thing we're going to look for is we're going to look for the difference of two squares. So what I mean by that is, okay, and sorry, I keep getting interrupted here. The factoring, we're looking for the difference of two squares, but this is not, it is a difference, but 8 is not a perfect square. X to the 9th is not a perfect square. P cubed is not a perfect square. So then we might want to look for the difference or sum of cubes. So we look at this and we say, 8 is a cube. It is 2 cubed. X to the 9th is a cubed. It is x cubed times itself 3 times, because you would add those exponents. And same thing with these. If you'll notice, these exponents are multiples of 3. That's a good clue. So I'm trying to remember. I think when you have something cubed minus something cubed, it factors into the a minus b times a squared, and I think it is plus, and then ab and plus b squared, like that. So if it's the difference of 2 cubes, then it factors into a minus, this is the same sign as this, a minus b, and then times this, a squared is the first term in this trinomial, ab, and then b plus is the last term, and they're both plus. And for the sum of 2 cubes, it is a plus b times a squared, and I think this sign here is minus now. That's the difference. So if this is plus in your sum of two cubes, then this is plus, but that is minus. If this is minus, the difference of two cubes, this is minus, but that is plus. And the last sign is always plus. So we just have to fit it into this mold, basically. We have to take this expression and fit it into one of these two. Something cubed minus something cubed. Well, we have minus. We know it's this first one right here. And we have to write 8x to the 9th as something cubed. And then that something is going to be our a. So 8x to the 9th. We need to write 8 as something cubed. Well, 2 cubed is 8. And x to the 9th as something cubed. X cubed, and then having that cubed would be your 8x to the 9th. Okay? 2x cubed times itself 3 times will give you 8x to the 9th. Minus, and then over here, y to the 6th and p cubed. If I have y squared and p, and I cube that, that will give me my y to the 6th and p cubed. Now, here's your a, and here's your b. You just follow the formula. So it's going to be a minus b, or 2x cubed minus y squared p. And then it's going to be a squared, so it's 2x cubed squared, which would be 4x to the 6th, plus ab, so just multiply these two terms together, 2x cubed y squared p, and then plus b squared. And that's going to be the y squared p, which is going to be y to the 4th and p squared. Put parentheses around that, and you are done. Okay? You can try number 12. Let's go down here to 106, and the instructions are to solve. Notice that in this number 19 here, this is lesson 106, we have a system of equations where there are 3 equations and three unknowns, x, y, and z. Not every equation has to have all 3 variables in it, but there are 3 different variables in 3 equations. There's lots of ways to solve this, but one of the easiest ways is to use a method of either substitution or elimination or a combination of both. Okay? So you can do this and approach this many different ways. As long as you are algebraically sound, you'll be fine. Let's take 2 of them at a time, and take 2 at a time that have a common variable, eliminate that variable, and then take the resulting equation with the third one that we didn't use, and use elimination in that one to narrow it down to just one variable. Once you have the value for one variable, you can plug it back into where you can solve for a different variable, and then take those 2 values and plug it in and find the third one. So here's what I mean. I'm going to take these 2 equations right here, because they both have an x and a z, x, oops, sorry, as x and a y there. Oh no, that's fine. I can do that. I'm going to take these 2 right here, because they both have an x in them. And I'm going to eliminate that x. Here's what I mean. X minus z equals 3, x plus 2y equals 5. I'm going to basically subtract those 2 equations. I've lined them up so that everything that is like is aligned, and I'm going to subtract those 2 equations. X minus x, they cancel. That's why I'm doing this. Minus z minus 2y, and 3 minus 5 gives me a negative 2. That is my resulting equation by subtracting these first 2 right here. Now, my resulting equation has a y and a z in it. Maybe I'll write this as negative 2y minus z equals negative 2. And I'm going to take this one right here that has a y and a z in it. So y plus z equals 0. And this is beautiful because I have everything lined up, and I notice that the z's are opposite. I'm going to add them together. So negative 2y and positive 1y is negative 1y. Negative z and positive z cancel, and negative 2 and 0 is negative 2. I divide both sides by negative 1, and I end up getting y is 2. Once I know what y is, I can take y and put it back into any of the equations and solve for the other variable. For example, I can take this y and I can put it in right here and solve for z. I can take that y and put it in right here and solve for x. I can take that y and put it back up here and find the z up here. So whatever you need to do, once you know that y, you can plug it in and find the z, or you can take the z, once you know the z, then you can plug it in there and find the x. Okay? And you're good. So you can find one like that and try that on your own. Okay? All right. Let's do 105 here, number 29. Negative 2x plus 8x cubed. Okay, we're going to solve this. Notice it says solve by factoring. So anytime you factor, you're always going to look for a common factor first. Always, always, always. I'm also going to arrange these in descending order according to the exponents. So I actually want to write this as 8x cubed plus 6x squared minus 2x equals 0. Then I'm going to look for a common factor. That common factor is going to be a 2, because 8, 6, and 2 are all multiples of 2, and an x. So I'm going to take out a 2x. When you take out 2x, don't leave a 0 there, okay? It's 1. The way you can always check is if you were to remultiply this 2x by all three terms in parentheses, you should get what you started with, okay? Okay, now I'm looking to continue to factor here. I have a trinomial, and I want to factor that trinomial into two binomials. Don't forget this 2x, it's still there, but I'm going to factor this trinomial into two binomials. Sometimes this takes a little bit of guess and check, and you still are looking for, when you FOIL these two binomials, you want to get this trinomial up here, okay? So let's just do a little guess and check here. You know this is the easiest one to start with. In order to get negative 1 here, these two values that are the last in the parentheses have to multiply to give you a negative 1. Well, the only way you're going to do that is to have a plus 1 and a negative 1. So that's an easy start. Then, this 4x squared, you know you have to have an x and an x there. And then how are you going to get the 4? It could be 2x and 2x, or it could be 4 and 1. But look, you want to get a 3x here. And where does the 3x come from? The 3x comes from the outside product plus the inside product. So I want to have a 1x here and a 4x there. How did I know that? Because when I go outside, that's going to be a negative 1x, and I go inside, that's a positive 4. They add together to give me the 3x that I want. Okay? Now what we do is, any of these three parts can produce a 0, and when you multiply them all together, you'll get 0. So you look at this and say, okay, what if this first part is 0? What if the second part is 0? What if the third part is 0? Any of those parts, if they become 0, then you multiply them all together, you'll get 0. So here are your possible solutions for x. I solve each of those parts when they're set equal to 0. I solve them all. And here, x would be 0, x would be negative 1, x would be add 1 divided by 4, 1/4. Those are your three values, the three solutions for number 29. Okay? So that takes care of, I think I did 105, I think I did 106, 107, 108, 109, and 110 by looking at those problems. If I missed something, please let me know. 105, 106, there's 108, 109, 110, and 117. Yes, okay? All right, so now I'm going to go on to 115, and I am only going to look at 111 to 115. Okay? So anything 111 to 115. let's look at, actually let's do this in order. So let's find the 111. I'm not going to do that one. 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 I don't see a 111. So maybe we'll have to come back to that. Alright, we'll come back to that. Let's go 112, 113. Let's just do these right here. Okay, here we're talking about, oh, these are great problems. Love them, love them, love them. We're talking about logarithms here in 113, 115. So, remember that a logarithm problem, you're either going to find a logarithm or an anti-log. Let's first of all talk about what that is. When we talk about a logarithm, or log for short, log basically means exponent. That's what it means. Log equals exponent. Okay? If you write 10 squared equals 100, well, 10 squared equals 100, if I then say, what exponent, what power of 10 gives me 100? Or, what exponent? I want to know what the exponent is. That's what log is all about. Give me the exponent that I would raise 10 to in order to get 100. The way we write that is, that question, the way we write that question in mathematics is we say the log of 100 in base 10 equals what? And the answer is 2. Notice why I'm saying log equals exponent. When you take the log of a number, you're asking what is the exponent. But you always have to know what base you're working in. In other words, this number 10 is your base. So this 10 down here written as a subscript, that is your base. Now, if I don't write the 10, it's understood to be base 10. That's called common log. It's so common. So if I just write log of 100, it's understood to be base 10. And the answer there would be 2. So you have to be able to go from exponential form to log form. Notice the base here is written as a subscript. The exponent is here, and that number you're taking the log of. The log of 100 in base 10 equals 2. That's how you read it. So, right here, this and this and this one, they're all dealing with logs. Even this one too, because it's a power, 10 to a certain power. Okay? So, let's look at how we... Okay, I'm going to pause and get a new sheet. Okay, I'm back. We are talking about number 6 here, log. So I said that log equals exponent. And if you're in base 10, it's called a common log, just log. Notice that some of these have a base with a letter right there. It's called e. That's base e. E is a number that comes up often when you talk about compounded interest. The actual value of e is something like 2.71, yada, yada, yada. It goes on and on and on, I think. Okay? If your base is e, log base e, that's called natural log, and it's abbreviated as ln, log natural. Okay? So let's just talk about how we work with logs, how we solve logs, how we evaluate logs. Right here, number 6, x equals natural log of 0.0076. You basically are just going to take your calculator and find the ln button on your calculator and punch in 0.0076 and take the natural log of it. Okay? What this is asking you, remember, log equals exponent. It's asking you to find the exponent. In other words, e to what power? E, because it's natural log, to what power is going to give you 0.0076. That's what it's asking. You just punch it in your calculator and you'll get it. So number 7 e to the x equals 92.6. Okay, again, it's asking you find that exponent. What is this exponent right here? Just another way of writing it by saying find that x value. Well, that x value is an exponent. Log equals exponent. So I'm asking the question, the natural log, because it's base e, I don't need to write e down here. ln takes care of that. The natural log of 92.6 equals what? Plug that into your calculator, and you got it. Okay? Number 8. Number 8. Let's do number 9 first, because number 9 is the same lesson. LOG, common log, base 10 of x equals 3.412. So this is saying, remember this would be 10, we don't write it, but it's base 10. So it's saying x, the exponent, sorry, this is the exponent. This is the exponent. Log equals exponent. This is your exponent. So it's saying the number x is going to equal 10 to the 3.412. You plug that into your calculator, and you're good. Okay? Number 8. Number 8, 34 equals 10 to the x plus 3. All right, 34 equals 10 to the x plus 3. Well, remember here, you're adding these exponents. You add exponents when you multiply powers. So what this is saying is 34 equals 10 to the x times 10, that's a 10 there, cubed. Split that apart. Give each of them a part of that sum in the exponent. 10 to the x, that's the first part, times 10 cubed, that's the second part, because if you multiply these together, you would add those exponents, x plus 3. So, this is just a number, this is just a number, let's bring them together. 34 divided by 10 cubed is 1,000, equals 10 to the x. You're trying to find the exponent. If you're trying to find, anytime you're trying to find the exponent, you are taking the log of something. So you're going to take the log in base 10, I'm not going to write it, of this number, 34 divided by 1,000, 34 divided by 1,000, 1, 2, 3 is 0.034 equals x. Ask your calculator what that equals, and you got it. Okay? Alright, hold on a second here. Alright, let's use our knowledge of logs and exponential growth to solve number 11 and 12 here. This is lesson 115. We kind of touched on 115 right up here, but let's deal with these word problems. So number 11, deposited $100 at 9% interest compounded continuously, and how much money did she have at the end of 9 years? The initial, the rate. Okay, this is a problem with compounded interest, and this is where that value E comes in. E comes in because when something is compounded over and over and over, it builds upon itself and it explodes exponentially, and that value of E comes into play. Maybe we can talk about how E is actually calculated. But there is a formula, and here's the formula. You can just think of A PERT. So A is the amount after time t, so sometimes you see a little t there. The amount after time t. P is called the principal or the initial amount. E is the value 2.7 whatever, okay? R is your rate of interest, your rate of compounding, and T is time. So, let's look at does time have to be in years, or I think it might be in years here. Hold on, let me double check. Okay, yeah, time is going to be in years for this equation. So here we go. You deposit $100. That says initial amount. That's your P. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . okay? And at 9% interest, but you're writing that as a decimal. So it's 0.09. How much money did she have at the end of 9 years? 9 years. So this is going to be your 9 here. You take your calculator, you take 0.09 times 9, and then you take e to that power. There should be an e button on your calculator if you have a scientific calculator. E to that power, and then multiply by 100, and you will have the amount that you have after those 9 years. Okay? The same is true for populations. So populations increase exponentially. What that means is that something is going to increase slowly at first, but then because it's building upon itself and branching off and expanding rapidly, it's going to then explode exponentially after some time. So number 12 is saying, same idea here. This is how you want your money to grow, by the way. So it's going to grow slowly at first, but if you have it in an interest-bearing account that is compounded, maybe monthly or quarterly or whatever, it's going to then grow exponentially over time. At first, there were 16,000. So 16,000 is your P, your initial amount. 3 years later, there's 60,000. They're actually giving you the amount now. They're telling you that 60,000 is how much you have after 3 years. R, and this is 3. So in this problem, we don't know R. We're going to have to find R first, and then use that R to find out how many people there'd be after 10 years. So you have to take 60,000 divided by 16,000, and that equals e to the 3r. Okay? Now what you have to do is, you don't know what this exponent is. How do you find exponent? Log equals exponent. So I have to take the natural log of 60,000 over 16,000, whatever that is, and that is going to equal 3r. And so now I take my calculator, I punch in 60,000 divided by 16,000, take the natural log of that, divide all of that by 3, and I will have my rate. Once I have that, I'm going to then continue the problem and find out how many people are there 10 years later after the initial 16,000. So now 16,000 is still my initial. E to the rate, you're going to take that rate that you just found, whatever this value is right here, that is your rate, and multiply by 10 this time, whatever value that is would be your answer. Okay? Alright, let's scan down here. Let's find, yep, we need to do 114. So 114, the coordinates of the points in which the area is designated are satisfied a given system of inequalities. Okay. Alright, so it's asking us, you have a circle, it's actually drawn for you, which is nice, and a parabola, which is drawn for you, which is nice, and it's asking you which of the regions on this particular graph is going to satisfy this system here. Okay? So it says you're basically going to be inside the parabola but outside the circle, inside the parabola and inside the circle, outside the parabola but inside the circle, or outside the parabola and the circle. Okay, A, B, C, or D. So really all you need to do here is, I would suggest you just first of all understand how these graphs were drawn, and then we're just going to test some regions. So here, this is a circle. This 16 is the radius of the circle squared. So you'll notice this circle here, its center of the circle is at the origin because it's just x squared, not x plus something squared or x minus something squared. It's just x squared and just y squared. So anytime you see just x squared and y squared, the origin is your center, and then it is going to be this number on the other side. If it's in this form, that is your radius squared. So notice the radius is 4. Okay, the radius is 4, and you would put that center and draw a collection of points, all of them 4 units away from the center. This parabola here, y equals, anytime it's y equals, it's going to be a parabola that opens up and down, up or down I should say, okay? And then it's x squared plus 4x plus 2, and that then determines where the vertex is of that parabola. It determines how much it opens. Is it open really wide or narrow? And I think you'll be getting into that later on. So all we need to do here is look at the different possible solutions. So here's a great one to test. C would be really easy to test right away because this point 0 is in the region of C, outside the parabola but in the circle. And if I put 0, 0 into both of these, it has to work in both. So 0 squared plus 0 squared is less than or equal to 16. Yes, 0 is less than 16. 0 less than or equal to 0 squared plus 4 times 0 plus 2. And that is also true. So right away, woohoo, we got lucky there the first time. So it looks like the region that works would be right here. If one point in the region works, every point in that region is going to work. Okay? You can test other points. You could test this point right here, which would be what? Negative 2, 1. If you test negative 2, 1 in for x and y, negative 2 goes in for x, 1 goes in for y, it should not work. At least it shouldn't work in both of them. Maybe in one, but not in the other. Okay? You could test this region. You could test A up here. A, if you pick a point in A, it shouldn't work. You can pick any point in D, out here in D, anywhere in D, and it shouldn't work. Okay? Alright. Let's look at number 16, which is 112. It says graph on a number line. Graph on a number line. So we've got number 16, x squared less than negative 7x minus 10, and the domain of the real numbers. In other words, the solutions are going to be any real numbers. So x squared, and I'm going to bring all of the terms over to one side and leave 0 on the other side. So x squared plus 7x plus 10 is greater than 0. I'm going to factor this. So I know that to get x squared I need x times x, and 10 is going to be 2 times 5 or 1 times 10, and I know that I have to get a positive here, so they're either both positive or both negative, but I'm going to get a plus 7 when I add the outside and inside products together. So looks like I'm working 5 and 7. If you see this sum here is going to be, or 5 and 2 if the sum is going to be 7. So I believe it's just going to be 5 and 2. Then I find out where it is equal to 0. Those are going to, the values where it's equal to 0 is going to divide into the regions that I then test. So where is it going to be equal to 0? If x is equal to negative 5, this first part is going to be 0 and everything else is 0. So negative 5. If x is equal to negative 2, this second part is going to be 0 and everything else is going to be 0 because it's a product. So negative 2. And I'm going to have open circles because it's only less than, open, and open. And I'm going to test my regions now. I've divided into 3 regions here. Actually, it's really just 2 regions because it's either in between or outside. But and I'm going to test, let's take negative 3. Let's take the number negative 3. If I put in negative 3 plus 5 is 2. Negative 3 plus 2 is negative 1. And 2 times negative 1, is that going to be negative? Yes. So I'm going to shade in between. If you want to be safe and check something outside the inside region there, 0, 0, and 0. So 5 times 2 is not going to be negative. If I come down here below negative 5, negative 6, this is going to be negative, this is going to be negative. Negative times negative is positive, not less than 0. Okay? So, what else here? Okay, I think we're done there. I'm going to pause for a second, and then we're going to continue on. All right, let's pick up where we left off here. I'm looking at problem set 120, so we're going to look at 116, 117, 118, 119, and 120 if they're all here. And the first one we come across is actually 120. These are age problems, and the trick here is to write expressions that match what age they're talking about. Let me just show you what I mean. Number 3, it says a man is 18 times as old as his son. So I'm going to use M, the age of the man, and N for the age of the son. So man is equals 18 times the son, N. That's one of the equations you're going to use. In 15 years, now it's not just M and N. We don't want a new variable. Don't make a new variable. You still want to use only M and N, but in 15 years, the man's age is going to be M plus 15. The boy's age, the son, is going to be N plus 15. So in 15 years, he, in 15 years, will be 3 times as old as his son. So now we have to express both of their ages in 15 years. So M plus 15, that's the man in 15, will be 3 times, will be or is at that time, 3 times as old as his son at that time as well. And his son's age at that time is N plus 15. So you have 2 equations, 2 unknowns. You have to solve using substitution or elimination. It's just that easy. You could simply take 18n, and wherever there's an m in the other equation, you can put in the 18n, solve that equation for n. Once you know n, you can put it back in here and find your m. Okay? So you can probably do number 5 if you want to practice. Let's look at number 6, 119, absolute value, absolute value. By the way, this is your domain. I think Z, maybe Z stands for integers. R is for real numbers. So in this case, we're only looking for the integers. 1, 2, 3, 4, 5, 6, 7, negative 1, negative 2, negative 3, negative 4, negative 5. Here, you're looking for all real numbers, and so decimals, etc. It's because we're graphing here, okay? So this one, you put just dots on the integers on your number line. Here you would shade in. Let's look at the inequality though. You have to know that inequality means the distance from a particular point. So what this is saying right here, actually let's start with something simpler. When I say absolute value of x equals 16, or let's keep it simple here, equals 3, okay? Absolute value of x equals 3. What I'm saying is the distance of this point from 0 is 3. Well, what numbers have a distance from 0 equal to 3? That would be positive 3 and negative 3. That's what absolute value is telling us. The distance from 0 is 3. Well, that would be positive 3 or negative 3. So your solutions there are positive, negative 3. If you have then another value in here, like for example, in our case 3, what they're saying is the difference between x and 3, the distance, the difference between these two is, and I'm going to change this for a second. Right here, this says less than. I know it does, but I'm going to change it to equals just for a second, is 2. What we're saying now is the distance x is not from 0, but from 3 is 2. So now we would graph this and we put 3 there, and we would go 2 units on either side of 3. So now we're going to be at 5 and 1. So your answers there would be 5 and 1. Well, let's just look at this and see how we could get 5 and 1 from our solutions. Well, if you look here, hopefully you see that 3 and 2, if you add them together, you're going to get 5. If you subtract them, you're going to get 1. Well, how do we get that? We know when you have absolute value up here again, your answers were positive and negative. In other words, x was positive 3, but it also was negative 3. So if I take x minus 3 is equal to 2, or x minus 3 could equal negative 2. And I solve these two. This one's going to give me 5. That one's going to give me my 1. So we're going to continue that and do that even with the inequality. Okay? Let me get a fresh blank sheet here. Okay, so in our case here with number 6, we have absolute value of x minus 3 is less than 2. So that what this is saying is whatever number or numbers we're talking about, the distance of that number from 3 is got to be less than 2. Okay? So if we think about this, let's just look at the number line right away. The distance here between this number and 3 is going to be less than 2. So here's 3. If I go 2 units on either side of that, I am at 5 and 1. But I don't want to be exactly 2 units on either side of 3. I want to be less than 2 units, 2 steps away from 3. So that means I can't go above 5 and I can't go below 1. I want to stay in between that so that I am a distance of less than 2 from 3. All right? Number 7. Absolute value of x plus 3 is less than or equal to 2. In this case, notice an x plus 3. You really want to change this to a minus a negative 3, because that's really what it's saying. This has to be a minus here. You're trying to find out what's the difference between two numbers. The distance really is one number minus another number. That's how far apart they are. And again, we want it less than or equal to 2. Now, if I come back up here just for a second, if this had been greater than 2, guess where we would shade? We actually would shade not inside, but outside, and that means above and below. Actually, I did this incorrectly. If z here represents integers, I actually should be only shading the actual integers points on those integers and not shading it in. Sorry about that. So in this case, I want the distances between our numbers and negative 3 to be less than 2. So less than 2, I want to stay within 2. Actually, it could be less than or equal to 2. So I'm going to have a solid circle here, and I'm going to shade in between. Again, if this had said greater than or equal to, I would shade above and below, go outside that region. Okay? Let's come down here to number 9, lesson 116. How many different auto tags can be made by 3 letters followed by 3 numbers if no repetition is permitted? Both the letter O and the number 0 are allowed. Okay, here's what you do with this. This is a permutation problem. How many different combinations can we have given these letters and those numbers? So your license plate on your car is going to be having 3 letters. Let's make spaces. 1, 2, 3, and 3 numbers. 1, 2, 3. Lots of different combinations, obviously, because we have letters. We got 26 letters in our alphabet, and numbers 0 through 9. That's 10, because they say O and 0 are both allowed. Now this is key. No repetition is permitted. So once we use a letter, you can't use it again. If repetition is allowed, then you have a selection of 26 letters for the first 3 spots and a selection of 10 different numbers for the last 3 spots. And if repetition is allowed, then you would put 26 times 26 times 26 times 10 times 10 times 10 and multiply all those together, and that's how many different possibilities there are for the different license plates. But if repetition is not allowed, you'd have to go 26 Now you have to take whatever the first number is, you throw it out. Now you only have 25 options left. You throw those 2 out. Now you only have 24 options left. Now you go to numbers. You got 10 numbers, but you throw 1 out. Now you have 9 left. You throw 2 out. You got 8 left. You multiply all that together, and you have your answer. Okay? Let's come down here to, we did logs. Oh, look at this. I'm not going to do them, but notice right here, we're doing logs, and it's a tie into chemistry, talking about pH, the concentrations of hydronium ions there, that's so exciting. That's so exciting. We're going to be doing logarithms when we get into the upper chapters in chemistry, when we talk about concentration of hydronium and hydroxide ions. Very cool. Let's come down here to 118. 118, notice we're doing logs, but now it is in an equation, and we're going to be solving for our unknown here, x. So we're still going to be applying algebraic principles for equations, but now we're going to throw in our knowledge of logs in order to then solve for x. Okay? All right. 118, number 25. First of all, let's do this just for a second. Let's talk a little bit about some rules for exponents and also then the subsequent rules for logs. You know that when you take x times, or x to raise to some power times x raised to a different power, you would add those exponents, a plus b, like that. Well, if you're adding exponents, remember log equals exponents. Okay? So if you're adding exponents, if you have the log of a, or maybe I'll put n here, let's use n for number, the log of n plus the log of, m, if they're in the same base, base 10, when you add logs like that, you can multiply the arguments. Those are called arguments there. So this would turn into log of mn or nm, however you want to look at it. Okay? This goes both directions, either way. The log of a product, you can break it apart into the sum of the individual logs of those arguments, of those factors. Okay? Any other log principles that might pop up here? Well, let's just try number 25 and see what happens. So, log x minus 3, this is in base 4, minus the log of 7 in base 4 equals log 31 base 4. Okay? So on this one, alright, sorry, I just had to think about this one a little bit. So on this one here, we're going to apply this principle and the sister rule of that. The sister rule would be basically when you have two powers, let's say x to the a over x to the b, that is equal to x to the a minus b. So if you have log of m over n, that is equal to the log of m minus the log of n. So we're going to apply this one and this one down here to this problem. I'm actually going to try to bring everything over to one side, all these logs, and combine them together. They all have base 4. That's what makes me think I can combine all of these. And now I set it equal to 0. So notice we have base 4, base 4, base 4. They're all in the same base. Just like up here, these were all x or base 10 or whatever. So if I have the log of something minus the log of something else in the same base, those can become the log of the quotient of those two arguments. As well as I'm subtracting another one here of something else, so that also is going to be going into the quotient. So here's what happens. This is all going to be combined as the log of x minus 3 minus this log. That means the 7 is going to go in the denominator, just like I wrote up here. Okay? and minus this one, which means that argument, the 31, is going to go in the denominator as well. And this is all still log in base 4 is equal to 0. Now I have x minus 3 over 7 times 31, and I'm going to write this now in exponential form. Remember, this base is 4, and log equals exponent. So this is my exponent right here. So I'm going to rewrite this as the argument equals the base raised to the exponent. Anything to the 0 power is equal to 1. So I'm going to take 7 times 31, what is that, 217. And I got x minus 3 is equal to, I multiply both sides by 7 times 31, or 217. And then you subtract 3, and I think I get to 14. Okay? Now, of course, I could check that. I could put that back up here, although it's kind of hard when you're dealing with base 4. But I believe that is how we tackle that one. All right, there's one right here for you. You can try this on your own. This is all base E, natural log base E, natural log base E. They're not going to write the E there. Oh, 125. Ooh, looks like we got a lot of construction here and proofs. Not my favorite part of math, but we will outline these proofs for you, okay? I'll be right back. All right, let's continue here. We are in problem set 125, so we'll look for problems that deal with 121, 22, 23, 24, 25. Looks like we are dealing with proofs. And you're going to be starting with something that is given, and then through a series of steps, logical, reasonable, rational steps, you're going to have to get to the statement that they want you to prove. Okay? Now, I'm just going to talk through most of these. You would actually set up a situation where you have statements and reason, I believe it is, and you make your first statement and then give the corresponding reason for that. So that's kind of how I'm going to talk through these different proofs. I'll make a statement, I'll tell you the reason, statement, reason, statement, reason, statement, reason, and it's got to go step by step. You can't take leaps. You can't make a statement that goes way down here if you can't make that logical step. You've got to do it in incremental steps, and they have to be based upon what you already know or what you're given, or what you can prove with the diagram or the given information. So we got a circle, and you have that PR. It says PR is perpendicular to ST. So if we started with that statement right there, the reason would be given. Then we could say that angle PRS and angle PRT are right angles, and that's because the reason would be perpendicular lines form right angles. And then you could say that angle PRS and PRT are congruent because right angles are congruent. You got to go step by step. I know it's kind of tedious. Then it says here that you want to draw QS and QT, and now we can say that Q side QS and side QT are congruent because radii, they're both radii. Radii are going to be equal in length and therefore congruent. So now we've got a pair of, we've got sides that are congruent, we've got angles that are congruent, and we probably need another side. So this here, QR, this little segment QR is a part of both of those triangles. So you know that QR is congruent to itself, and I believe that's called reflexive property. So now we have this little triangle here and this little triangle here. They have in common, or they have congruent, a side, another side here, and an angle. And one of the the theorems that shows that angles are, or that triangles are congruent, I believe is side angle. I don't think so. Hold on, let me check. Okay, I think these two small triangles right here and right here would be congruent because they're both right triangles, and we have the hypotenuse and a leg are congruent. So hypotenuse leg is a theorem for congruent triangles. That's only true for right triangles. So anyways, we've got these two small triangles now congruent to each other. Then we can say that side SR and side RT are congruent because they are corresponding parts of already congruent triangles. We've shown that the two small triangles are congruent, but we didn't show that SR and RT are congruent, but now we can say they are because the corresponding parts of congruent triangles are congruent. CPCTC. Now we have this side, those two sides are congruent. We again have these 90-degree angles here. So now the big triangles, those big triangles are the ones we're looking at now. So we want to look at, we have a side here, SR and TR. We have angle, we still have that angle there. And now this long side, PR, we would say PR is equal to itself. That's because reflexive. So now we have the two big triangles. We have side, angle, side. So now we can say triangle SRP and triangle TRP are congruent because of side, angle, side. And then we can say that angle S, which is part of this big triangle right here, and angle T, part of this big triangle right here, are congruent again because CPCTC. Whew. All right. So you kind of get the idea of how we walk through these proofs step by step. I'll do one more for you. Let's try this one. So we would probably state these things here first. Those might be our first three statements. And then for each of those, our reason would be either given. So let's just mark it on the diagram here. BE is congruent to BD, and BE is perpendicular to AE. Okay? So what that's going to lead us to say is that with this angle here, AEB is 90 degrees and therefore a right angle, and BE is perpendicular to AE. And we want to show, and then BDC is a 90-degree angle. So that's a 90-degree angle. So basically what you're going to say here is outline the proof. We want to get all the way to AED. AED, we want to get to this angle, and CDE, this angle, are going to be congruent. Okay, so here's what we're going to do is we've got two 90-degree angles right here, and I would like to prove that this angle in here, those two angles, are indeed congruent, because then I'm going to be adding the same amount to these right angles and then show that the angles in question are indeed congruent. I have a side. Okay, so here's what we would do is right here I could state that I have an isosceles triangle. So this is an isosceles triangle right there because those sides are indeed the same length. And then I would say that this angle right here, BED and BDE, are congruent because the base angles of my isosceles triangle are equal. Okay, so you say they're equal in measurement and then they're congruent. Then I could say that this angle here, AEB, plus this angle BED, and I can use substitution to show that that is going to be the same thing as CDB and BDE, and show that then this angle here and this angle here are indeed equal in measure and therefore are congruent. I don't know if you picked all that up, but it's a little convoluted and confusing. But I think you'll be working on proofs more, obviously, in the next lesson or the next level, and we'll pick up more of this. So I'm going to move down a little bit further and talk about constructions. That is basically using a straight edge, a ruler, and a protractor and a compass to construct angles and bisect angles and construct triangles and things like that. Just using these three instruments. That's all you're allowed to use. Okay? So I'm just going to briefly talk about some of these here. These are all, looks like all in lesson 123. Construct a triangle whose sides are 4, 3, and 2. What you would do here is you would take your ruler and draw a straight edge that is 4 centimeters long first. Then you're going to take your compass and open it up to an opening that is exactly 3 centimeters. So you place this compass here, the 2 points of your compass, on your ruler and open it up so that it's open exactly a distance or an opening of 3 centimeters. You take your pointed end of your compass and open it up and keep it at that 3 centimeters and put the pointed end at one end of the segment, and then draw a arc using the other end where the pencil is, and that is going to be 3 centimeters. Okay? Then you're going to take your compass and open it up to only 2 centimeters and do the same thing, but put it at the other end now, the pointed end at this end, and draw an arc here of 2 centimeters. So this is all 2 centimeters, and where they cross, that's going to be the vertex of your triangle, and you can draw your 2 sides. Okay? Constructions are kind of cool. Number 7, use a ruler to draw a line segment 4 centimeters long. So just like we did, construct a perpendicular to the segment at the point on the segment that is 1 centimeter from the left end point. Construct a perpendicular to the segment at the point on the segment that is 1 centimeter from the left end point. Okay, so if I understand this correctly, we're going to draw a line segment 4 centimeters long, construct a perpendicular to the segment at the point on the segment that is 1 centimeter from the left end point. Okay, left end point, 1 centimeter, we've measured 1 centimeter. And basically what you're going to do here is you are going to go the same distance on either side of this point right here and take your compass So if you went, it really doesn't matter. You've got a point here. We just need another point either above or below that is going to be equidistant from this segment. So you are going to pick, if this is 1 centimeter here, you're going to go 1 centimeter on the other side of that point. So this is like 0, 1, and 2. And you're going to open up your compass. You can actually open up your compass to any opening you want to. It doesn't have to be particular. But you're going to take the pointed end of your compass and place it here on the 2 and draw an arc. Now don't change the compass. Keep it at the same opening. Go to the other side, put your pointed here, and draw an arc. And those then are going to be equidistant from, or this point here is going to be equidistant from the 2 points on either side of the point that you put at 1 centimeter. And then just draw a straight line down. Okay? Draw a line and a point that is not on the line. Okay, draw a line and a point that is not on the line. Draw a line and then a point that is not on the line. Construct a perpendicular to that line that passes through the point. In this case, what you're going to do is you want a line that's going to go straight through this point and be perpendicular to the line down here. Alright, so, oh yeah, I think the way you do this one is you open up your compass a certain amount, it doesn't matter, and you open up your compass, but this time you put the point on this dot and you draw an arc that's going to go through that line at two places, here and here. Then you change the opening on your compass and you go on these 2 points that you just made on the line and you draw an arc. You can make it open it bigger or smaller, doesn't matter. And you're going to keep it the same on both sides here. Place your compass on this point and draw your arc. I opened it really big, and then come over here, place your compass on this point and draw it really big. Okay, I opened it really big, and I should have my arc then, my 2 arcs crossing, and now I'm going to draw through that point that was formed and the point that was already existing, and I should have a perpendicular line. Okay? Let's do one more here. Use a protractor to draw a 36-degree angle. So you can take this device, your protractor, draw a line, and then put the straight part of your protractor on that, and the edge of it there at that point. Measure 36 degrees, okay, and put a point, and then draw your 36-degree angle right there using your protractor. Now it says use a straight edge and a compass to construct the bisector of the angle. The bisector of the angle. The bisector is going to go right through the center of that angle, like that. And I think, if I'm not mistaken, you're going to take your protractor, open it up a certain amount, and put the pointed end at that point and draw an arc. Now you have 2 points here. And now what you're going to do is take that compass, and you really don't have to change the opening, you can, but put it at this end, draw an arc, and then put it at the other end and draw an arc, and wherever those 2 arcs cross, that is going to form your angle bisector. Okay? Alright, that's good enough for construction for right now, and I think that takes care of everything 121 to 125. Alright, the last set here is dealing with problem set number 129. So I'll look for problems that go 126, 127, 128, and 29. Anything here? What? Huh. Problems at 129, I thought there'd be... Alright, I guess not. Because we covered 123, 124, we covered all of these already. So, we're going to stop right there. Alright? And so really, with this video, you've gotten up to lesson 125. You're going to be great. Alright? So if you watch the video, if you picked all this up, wonderful. If you want to try a few of those in there with the same lesson numbers, fantastic. But you're going to now drop Algebra 2, not drop it, but conclude it, finish it, wrap it up, and move on into advanced math. And Finn, let me know if you need anything as you move into advanced math, okay? I'll make as many videos as you need, as many videos as you want. We'll Skype, we'll talk, whatever you need in order to help you succeed and stay on pace, stay on track so that you're not doing math over next summer, which would be nice, right? Okay. Keep up the good work. Let me know how I can help, and check in once in a while with chemistry as well. Let me know what you need there. All right. See ya.